Page 204, number 23. So we have looked at this unit circle, and in this unit circle, we have identified the sine, cosine, and tan ratios in here. So the sine ratio is going to be the vertical length. This vertical line is the sine ratio. This horizontal length here is the cosine ratio. And then this vertical length here is the tan ratio. Okay, so it says determine a line segment from the diagram whose length is equivalent to secant theta. So secant theta is related to cosine, and secant theta is going to be the same as the x over the radius. Okay, now to work out the radius over x. Got that backwards. Okay, cosine is x over radius, so the secant is the same ratio as the x position over the radius. So it's going to be this line here over that line there. Now, it was nice we could use the unit circle in that when we had the radius as 1, the x value was cosine. In fact, that's how we defined cosine in the unit circle. Now, in this case here, before we had 1 in the radius as 1 in the denominator. To work out the secant as a distance in the circle, we need to have x as 1 in the denominator. So if I want that, I'm going to use the exact same triangle. So I'm just going to highlight the original triangle. This is my original triangle here. And I'm going to use the same similar triangle, but the bigger triangle, and use the same ratios. And the reason why I'm doing this is because if I take a look at that big green triangle, the x in that big green triangle, this length here, is equal to 1. So if I can use that 1 value in the denominator, then the secant value becomes the actual length. So remember that it was the radius over the adjacent. Well, the radius in this case is going to be equivalent to that line there. So that line there then becomes the same as the radius in that ratio. So I'm going to call that OQ. So that line that goes to the tan line, the length of that line then is going to be the secant ratio. So we're going to then say that the secant theta ratio is equal to the length of the line OQ. Okay, so that's how we can generate secant. And we can do the same thing for cosecant and cotangent as well. Okay, just going to clean that up a bit. Now, we've been asked to construct a line that is horizontally, this horizontal line here, tangent to the circle. Okay, so there's our line, and then the location of that dot is going to help us identify the angle theta, and then we could use cotan. So first of all, let's look at cosecant. Okay, we identified sine as the y coordinate over the radius. So the cosecant is going to be the radius over the y. And to get the length cosecant, we want y to be equal to 1. So I'm going to highlight this triangle here. And I want you to notice that this triangle is the exact same triangle as our original triangle that we started with at the very beginning. Okay, this red triangle that I'm going to highlight here. That green highlight triangle is the exact same proportions. So I can use the length in that triangle, but the reason why I want to do that is, notice that I wanted the y to be equal to 1. Well, in this triangle, this y value is equal to 1. And as long as I get the right sides here, I can then work out what the cosecant ratio should be. So in that picture, I'm just going to erase that red triangle for a second. In this picture here, this line would represent the same line that's equivalent to the radius. So I'm going to write that same ratio as OP is equal to the radius in the smaller triangle. And now in this case, the vertical line y is equal to 1. So that line OP then must represent the cosecant ratio. That line is equal to OP. And then we're going to do a similar reasoning for the cotan. Before we had the tangent, I'm going to need some room here. So the tangent was defined as the rise over the run. The cotan we're going to define as the run over the rise. And again, we want to have that denominator equal to 1. And if that denominator is equal to 1, whatever's in the numerator must be the same value as a cotan. So to make the rise equal to 1, we're going to again go back to that same triangle. Because in this green triangle here, remember that the rise was equal to 1. The y value is equal to 1. Well, then if that's the case, then this value here, it's not the x coordinate. We don't want to mix things up. It's a horizontal value. This horizontal value must be the run. And so that distance from that point right here to P, and maybe I'm going to have to label that point, and maybe I'll give that point, let's call that PQ, let's call that R. That distance from R to P then must be the piece that I want for that triangle. R to P, and that means then that length R to P must be the cotan length. So we're going to say that cotan theta is going to be the distance from R to P, okay, which is that one that I've kind of highlighted here. I'll kind of mark that a little bit darker, but that's the line we're looking at. That line, the length of that line, then represents the cotan of the angle theta when we have this theta position moving in this direction, identifying that point here.